Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master. Refath Bari. Watch his videos to achieve your dreams.
Hello folks, welcome to lecture number 25 of linear algebra. Today we're going even deeper into, actually we're not. Today we're changing subjects from dot products, Cauchy-Schwarz inequality, and all the other inequalities we learned to something very exciting, matrices. So today is kind of a transition lecture. So to get you started with that, today's due now is kind of a review. But if you forgot, it's also kind of a new thing. So, okay.
I'm expecting something insane because I can't trust you anymore after what you did to me in like lecture 24, 23, and 22.
Yeah. So just go ahead, do your best. If you don't remember, that's totally fine. Because but please remember we did this many times in the first few lectures. No, I'm just telling you. Okay folks, let's see what we've got. Our one student here showed, I'm not sure what. Our other student here, wow, he did remember that the column picture begins by taking a linear combination. So that's always good when we see a student remembering. Oh, you want to do it on the board?
Is that the expansion?
Very close. Yeah, it's basically the expansion.
So x times the vector 1, 2. And that's basically how many 1, 2s you need. Plus y to make the 1.
Be careful. Okay, so that's almost close.
Almost close.
Okay.
Wow, that sounds really bad.
Why doesn't our other student also try? Perhaps
yeah, give me my marker.
No, it's fine.
I'm generous.
Perhaps he wants a shot at expanding.
Yeah, I'm not quite sure what he did.
Yeah, that's not really, I'm not sure that's proper mathematical notation to start with. Anyway, our student here made a crucial mistake, a crucial error. This matrix is symmetrical, meaning that if you take it by rows,
1, 2, 2, 1. Oh.
so if you take it by rows or columns, you'll get the same answer.
Right.
Unfortunately, we actually multiply in a different way. Okay, we actually expand in a different way. We take the first row of our vector and the first column. Right?
Oh, where'd my board go?
We take the second row of our vector, take the second column. Right? Now it's become almost very easy. X times this vector is what? What is x times this vector?
You have got to be kidding me.
Do you know? Very good. And what is y times that vector? Very good. And what does that equal? Very good.
You
Wow.
literally.
Perfect. Perfect.
Oh, I did it.
You just copied what I said.
I did it.
Nice.
So our student here got the correct answer, and he did it all on his own, which is even better.
No, I think he copied me.
So great job.
Alex!
So as you can see, that's our answer. So if you forgot how to multiply a matrix by a vector, please watch our first few lectures where we cover this in depth, because we're going to be dealing with this a lot in this lecture and in future lectures. So why don't we go ahead and get started with the
I
lesson.
wish we could just get finished with the topic and switch to something else, because this is kind of starting to get a bit complicated and a bit messy,
So our lesson today is really designed to get you excited about using matrices.
Oh no.
So our lesson is going to start
Alex, I'm scared.
with a very basic question.
I'm very scared.
Okay.
Isaac is smart, so yeah.
So our lesson is going to start with a general question today. Usually we start with a specific question. Today I'll start with a general question. If I have a point A comma B, actually, you know what? I'll call it X comma Y because most people use, X and Y. If X and Y is rotated, hopefully you all know what rotations are,
Yeah.
is rotated by this angle.
Is it rotated around anything?
Yes, I will mention that in a moment. Why don't I give it like a Greek letter? Okay?
Rotated with respect to what?
Rotated by alpha degrees around the origin. Okay? Where will we end up? What is the resulting point? What is the resulting point? Resulting point.
Well, the resulting point is.
Alright, so that's our question. So our question is
So what is it? If X comma Y is rotating alpha
around the origin, what is the resulting point? So of course, the first step is to understand what the question is asking. If you don't understand it algebraically, we can always look at it geometrically.
Sure.
Okay, so geometry is always our best friend when it comes to understanding what a problem is actually trying to tell us. So let's say we're in the coordinate plane, right? And let's say I have a point. Okay, so let's say I have a point. Maybe I can call my point X comma Y.
Yeah, sure.
Okay, now let's say I rotate my point around the origin. Right, that's exactly what I said I was gonna do. So let me rotate my point around the origin. Okay,
How much?
by alpha degrees. So this is kind of like a general example. So I rotated my point around around the origin, and yes, that's exactly what we want to figure out.
Oh, really?
What are the coordinates of our new point? That's what we hope to find out. And hopefully we can answer this question using matrices, something we already know very well. So this is our goal, to find the coordinates of the new point after rotating the old point by alpha degrees around the origin. So we've conquered the first step, we've understood the problem. So now what can we do? We can start to think about solutions, right? What is, when we deal with rotating things, we think
pieces
about,
just don't fit together. Graph geometry and matrices, they
Well,
just don't fit together.
there's a way we can connect them maybe. Perhaps you have all heard of polar coordinates, right? Whenever you
I
see,
heard about polar bear.
oh no,
Polar bear or
So-
a polar bear. I
whenever
mean,
you
you
see,
gotta learn to pronounce things, Alex.
yeah,
Okay.
so whenever you see rotations, you want to start thinking, or at least considering, polar geometry, right? So let me give you a very brief crash course on polar geometry.
What a
So
polar
instead of
bear
polar
is.
geometry, why don't you call polar bear?
Oh no, it's not my decision, mathematicians. Okay.
You didn't blow out the gun ball, did you?
Yeah. So polar geometry is very easy, and hopefully we can answer some questions about it. So let's say I have, what is it? This is just a point, and I'll say the distance from this point to the origin is r. Okay. So now using polar geometry, right?
But we know that R must be always the same.
Let's call this point x comma y, shall we?
But if we rotate
One
360
second.
degrees,
Just one
then we
second.
know that this formed a circle, meaning that R must be the same. The distance from the origin must be always the same.
Okay, let's see. So this is r, and maybe I can call this theta. How can I express this this leg right here in terms of r and theta? Do we have any ideas?
X.
No. In terms of r and theta, how can we express this leg? We can call it r.
Sokatoa.
So Sokachoy, yeah. Which one should we take?
So this is
So
in terms of R and X, right?
Yeah.
Toa.
So if you do the work, you'll find this is our cosine theta, right?
That's true.
That's right. Because
X is cosine and Y is sine.
so this would be r sine theta exactly. So
That's not how you write theta.
yeah. So
There's a new way now.
this is our cosine theta. This is our sine theta. So instead of writing x comma y, what's another way I can write x comma y?
R sine theta, R cosine theta, and R polar bear.
Oh, close. R sine theta. Okay, great. So you're probably still thinking, hey, what does this have to do with matrices?
That's right.
Well, that's exactly what we're gonna get to.
Wait,
So now,
excuse me, I have a question.
yes.
So, if you rotate it
Mm-hmm.
by alpha degrees, say this is alpha degrees, I don't
Okay.
know how to write Greek letters.
Very nice.
So, then R would stay the same because this is a whole circle. R would stay the same.
Well, that's a very interesting point to consider. We'll come back to it at the end of the lesson, okay? So now, what have I shown you? I've shown you that x is the same thing as r cosine theta, and I've shown you that y
Is the R sine theta
is the same thing as r sine theta
according to the polar coordinate?
according to polar coordinates.
Don't mess
Now-
that up again.
Okay.
Why don't I just name this new point x prime y prime? And I want to find out what that new point is. Well, let me try to do that right now. Let's say x prime, and here is the very crucial idea. This is almost like magic if you watch carefully. So let's say my new x coordinate, x prime, is equal to r cosine, not theta, but theta plus alpha. Because
Oh.
see, I did a little boost.
Right, I did, yeah.
Okay. So why don't
I
I,
don't know how to write alpha.
so alpha, why don't I do it in red, you see?
Yeah.
So that's x prime. What about y prime? Well,
It would be the same.
Would
On
be-
side.
can you predict
Theta.
how much are we rotating y prime? Not just theta, but theta plus alpha.
Yeah.
So theta plus alpha. Okay, so hopefully we're starting to understand this a little bit, right? So now, do you?
No, from what I'm seeing, you could definitely also solve it using
Yes, but our goal is to use matrices.
Yeah.
Okay.
But
So,
we're not
do
gonna
you
do the
re-
matrices.
Do you remember how to expand cosine something plus something?
Yes.
Not really.
Well, let me show you.
Ooh.
You can say cosine of theta plus alpha is cosine of theta.
Why are you using
Uh,
brackets when it's not a vector?
Seems like we
or
don't have
matrix?
much space. This is equal to, let's factor out the r, right? So cosine
Why
of
are you
theta,
using brackets?
cosine of theta plus alpha is going to be cosine of theta times cosine alpha
Alpha.
minus, okay, so you want to be careful, minus sine theta sine alpha.
Right.
Okay, oh, and why don't I finish my brackets right there. But we are not done, right? We are not done. Why don't we expand our sine theta plus alpha? So can you please tell me what this will be?
Or cosine
Well,
theta.
let's actually find out.
Or
It's gonna
sine
be
theta.
sine theta cosine alpha plus,
Why is it
sine
cosine
alpha. well, these are just trigonometric identities you should memorize. Okay, so this is really nice. Now what I can do is I can distribute, right? Now, are you ready to distribute? Okay, let's get ready to distribute. Why don't I distribute in light green, which is one of my favorite colors. So r cosine theta, cosine alpha
I really gave you a variety.
minus r sine theta times sine alpha. Okay, now we're almost there. Why don't we distribute this one? Okay, so I'm gonna have r sine theta times cosine alpha, and of course, hopefully you don't get bogged down in the numbers. Keep in mind we're looking at the bigger picture here. Plus what? Plus r sine theta, r cosine theta,
You missed a lot.
times sine alpha. Now here comes the magical part. Okay, we've expressed
What is it the measure of sine theta plus cosine theta equal to 1?
not almost there, but I said that x equals r cosine theta, right?
You did.
I proved it. Well, instead of writing r cosine theta, I can just write x. I can replace all of this garbage by something neat. And hey, r sine theta is the same thing as
Why?
y.
Oh, x cosine x minus y sine x.
Yeah, and we see the same pattern here. R sine theta is the same thing as
Y
and r cosine theta is the same
x.
thing as x. So maybe you're starting to see a little pattern in the numbers. So what have we just shown? We've shown that x prime is going to equal x cosine alpha minus y sine alpha. Okay, maybe I can erase a little bit of my question to free up space. And I've shown that
I
y,
have a question.
yeah,
Do these only trigonometric functions have any relevance?
you'll see it just in a moment. So y prime is equal to y cosine alpha, okay, plus x sine alpha. Okay, this is the key idea. Now we have expressed our new coordinates in terms of our old coordinates. Now this is where matrices come in.
Really?
Yes. So, do you see the matrix?
Yes.
That's what you should see. So the matrix,
I was wondering why they were so
see,
similar.
this looks like a system of linear equations,
Yeah,
right?
system of linear equations.
And we know how to express systems in terms of matrices. So we can write this as a column vector. So just put them in, no big deal, right? And then remember the coefficient matrix,
X, Y.
and we only put the coefficients.
Okay.
So cosine alpha minus sine, you just drop them in. So there's no hassle at all. Okay, so let's make sure we got this right. Cosine alpha minus sine alpha, cosine alpha, positive sine alpha. Okay, times xy. All right, so we've correctly gotten the equations we needed, and it looks like we're good to go, right?
Yeah.
So y prime is equal to y cosine alpha. Okay, great. So folks, this is one of the many new identities we're going to learn, and we've just
Is
proven
there an
it.
isotop?
Yes, we've just proven it using matrix multiplication. So why don't we move on to our exit flip? Okay. Okay. Our exit flip. our exit flip will hopefully be a very easy review for you. So why don't we get started? So exit flip. Okay. So multiply, and maybe I'll just make this general. Okay. A, B, C, D, V1, V2. So hopefully that's a very easy exit flip, which will serve as a review. Do we have any idea what this could be? Good luck.
And then V1B plus V2D.
So a very good try. So let's see how we would actually do it. This is a very good idea, but unfortunately not close enough. We take the first entry of the column vector, multiplied by the first row.
Of course.
Okay.
Of course.
Okay. Looking better, but remember, this is a what? 2 by 2 matrix, right?
Yeah.
And this is a, how many rows? 2, and how many columns? 1. So the result would be a 2 by 1 matrix, which is indeed what you have. So very good job, and thank you for watching.
That's close.
Yes.
It's slower.
Subscribe to Bari Science Lab to fall in love with math and science, especially programs.